So, welcome back. How's homework 1 going, folks? It's not going? Would it be useful to go over anything related to homework 1?
So I don't know where it is. So I've gotten to the third model.
Great. That's the big one.
Yes, and so I think I'm stuck on now looking for like the simple slopes.
Okay.
So I don't know if that's like the middle. I've answered the last couple, but
Okay.
it's those. And maybe I just don't know how to do it in R, which could very well be it.
Okay. So for the simple slopes, you're writing out GLHT statements with 1s and 0s?
So I don't get the 1s and 0s.
You don't get the 1s and
Yes,
0s.
that's
Okay.
the part I'm stuck on.
Got it. Okay. Then we can work on that. How about we write out the model and talk about a little bit of logic? Would that work?
Yep.
Okay. And if you've already turned in your homework, now you can take a nap. So we have golf is a function of beta 0 plus what else is in your model here?
Let's see. I think there's group.
Yeah. So group is not one thing though, right?
No.
So we have control versus mini golf. So if I'm just going to make a shortcut there. So this is going to be the contrast that differentiates mini golf group from control. Okay. And then I need some more of those, right? This one was regular golf, and this one was both. Okay. And what else is in the model? I believe it is enthusiasm is one, and experience. And I named the mini golf enthusiasm scale the MGUS, because if someone asks you if you want to play mini golf and you don't really like it, you're like, I guess. So the MGUS is measuring enthusiasm for the sport of mini golf. Enthusiasm, we'll say, and experience, right? Yeah, now we got to put the centering in. So what is experience centered at? Oh, it doesn't like, it wants EXP to be like the math. So I got to do that. What's it centered at? 4? Does that sound right?
Yes.
That sounds right. Okay. And I said you could leave enthusiasm uncentered because the mean is 0 because it's supposed to be like standardized scale. All right, so this is the model in, I believe, section 2, right? So I got to add a bunch of stuff. So if we do that, and I'm hitting shift and enter to send it to a new line so that I can break it where I want to. And I need, is it experience is what it multiplies? That sound right? Okay. It's like I wrote my own problem. Because I think that the extent to which inconsistent training is going to mess you up depends on how much experience you have. That's my theory here. There. Did I get the numbers right? 1, 2. I skipped 3. I thought I had too many. All right. I did. Nope. At 1. There we go. Here we go.
We should have notified you a lot earlier that was a mistake, but we didn't.
You didn't. Well, then I won't feel bad that I can't count or type, but I am talking and typing at the same time, which is not easy to do sometimes for me. Devin, there we go. Okay. So, no! There. Okay, and there's an E at the end of it. We'll put it there for completeness, but E is not part of the story here. Okay, so let's say that we want to get one of the simple slopes. Like, give me one that you're working on.
Let's see, the of experience for regular golf.
Experience for regular. Okay. So, how do I get my ingredients here? What's my 3-step process? We want the slope of experience, right? That's what we're going for? So I need to do what in my equation here? I need to find all the places that have experience. So that one. All of those, right? Okay. What's next? Factor it out. The thing we want the slope for. Okay, what's left is my ingredient list. So if I want the slope for regular golf, what do I change? What goes here? What goes here? What goes here? 0. Okay, but I'm going to leave them in here. And I'm also going to do this to make another connection. Okay? So now, assuming that R outputs these in the same order in which they're listed here, the interior part of your call that has the 0s and 1s, what's the first spot going to be? Yeah, it's that one. So I'll give you a hint. If you're asking for slopes, the intercept is never, ever involved. It can't be. It's not multiplying anything. Okay, so 0 there. Next thing, do I need any beta 1? No, I don't. Do I need beta 2? I do not, and this is the tricky one, because you might be thinking, but it's the slope for that group, don't I need it? But this term does not have the slope in it, so it's not eligible to participate. Same with beta 3, same with beta 4. Do I need anything related to enthusiasm? No, not what I want. Okay, now we're up to something I need. Beta 5. How many beta 5s do I need? 1. How many beta 6s do I need? 0. How many beta 7s do I need? How many beta 8s do I need? There you go. That's how you do it. So it might be helpful to literally try to write that out first, and then you can see the pattern of what you're asking for. How would I do this in Stata? Lincom? And in Stata, I don't have to write 0s for the things that aren't there, so this gets a little bit shorter. How do I tell it I want beta 5? Yeah, the name of the variable. So let's say that I named it experience. So to make it look parallel in structure, I'm going to do this, because we need one of those. And then beta 6 is actually this whole thing. So I would type whatever I named my variables, or nope, Stata is hashtag, like that. And I don't need any of those, right? So technically, I could just skip ahead to the one that I need. So you only have to type the terms that have the 1 in them. What if I wanted to flip it around? What if I wanted the difference between control and regular golf at a different version of experience? Then I would have to start with beta 2 and then the relevant interaction terms. But instead of filling in which group it's for, I'd fill in what level of experience it's for in the spot that corresponds to which group I'm talking about. Okay, does that help? The 0s and 1s. Okay. Anything else that I can help with while we're on this topic? How to interpret the answers? So this number, you could have computed yourself from your output, but to get the standard error for the slope and the inference for it, we have to ask for it. And so you should get a corresponding p-value out of your output for this set of commands, and then that p-value is whether or not the slope is significant. So the sign of the slope is positive versus negative, significant or not is based on using an alpha of 0.05. And if the question choices are about benefits or what is it, benefits or costs? Do we have those question choices? That sound right? Improving performance or making performance worse? Then it's backwards. If the question is about performance, then lower scores are better. Keep that in mind. So a positive slope would make your golf score go up. It's not actually a good thing. Does that help answer your question? Okay. Any other questions? All right, then it's only Thursday. You got till Monday night. I will have office hours on Monday afternoon, and we have office hours tomorrow.
Yep.
And you have office hours on Monday or Tuesday?
Yes.
Okay, so Vladimir's off the hook. It's like, I already helped you all this week. It's going to be due. Also on Monday night, I find out if I have to show up to jury duty. So if I do, Jonathan is going to step in for me for that day, and he will have a different Zoom link, so I'll have to send out that information. And I don't know what's going to happen after that. I'm just going to be really unpleasant and try to get out of it. That's my plan. Okay.
When did you find out like what the case is about?
I don't know that either.
Could you just tell them you can't be biased? I mean, you are biased. You can't be unbiased.
Yeah, I will do what I can, I think.
Good luck.
Thank you, yeah. All right, then we're ready for something new. Welcome back to the actual name of this class, Generalized Models. And what is this, week 4 of the semester? Something like that? So the reason why I spent a month on not generalized models is because that was focusing on the X part of the model. How do you put the predictors in? How do you get them to tell you what you want, especially when there's interaction terms involved? The rest of the class, the hard part is going to be remembering what Y is, not X. Particularly in categorical outcomes, because Y can be on 3 different scales, and you have different versions of the solution depending on which version of Y you're predicting. So that's where the tricky part comes in. The good news is that everything that you just reviewed about how to fit fixed slopes and interpret them holds equally in this model. So all of that stays the same. So away we go. So big picture, what makes a generalized model? 3 parts. The big one that's different, actually there's 2 that are different, one that's the same. Non-normal conditional distribution. So rather than saying our residuals are normal, or that Y is conditionally normal after you factor in the predictors, we're going to say it's something else. And whatever something else is depends on what kind of outcome we have. So in most cases, we're not going to have residual variance as a thing anymore. It's gone. Because the normal distribution is one of the only ones that I've seen that has a separately estimated variance that is one number. Variance is going to be found as a function of the mean in most of these other distributions. So other distributions are more plausible for data that are categorical, or have boundaries, or have skewness. So the big switch is that in trying to figure out what model parameters make your data the tallest, we switch out the version of the formula used to calculate height. In standard linear regression, height is calculated using the univariate normal distribution. In a multivariate version of that model, we would switch to the multivariate normal. In categorical data, it's going to be either Bernoulli or multinomial. Those are distributions for categories. They're called discrete. Bernoulli is one that we'll see, count is one, and neither of these has variance as part of it. So variance is not a model parameter anymore. By the way, if you're reading the readings from Agresti, his book, he calls this the random component, and that is not the same thing as a random effect, if you're familiar with that term. So that's an unfortunate use of not synonyms. And the reason that we care about this is to get the correct standard errors and correct predictions. If variance isn't constant, if variance grows or shrinks as a function of the predicted mean, that means the standard error for everything should change too. So that's one change. We're going to switch out what distribution we're using for y to better match the scale of what y actually is. Number 2 is our friend a link function. A link function is a transformation. It is not a transformation of the data. Okay, we're not touching our data. Like when we predict binary outcomes, the columns of zeros and ones, that's going into the model as the outcome. We're not transforming data. What happens is that the link function is a nonlinear transformation of the conditional mean of the outcome to be predicted. Now I know that's a mouthful. So for example, if I have a binary outcome, pile of zeros and ones, the mean of a binary outcome is the proportion of people who have a 1. I can say that more directly as the probability of any one person in your sample having a 1. That's what the conditional mean is to be predicted. But what's the lowest that probability can be? 0. What's the highest it can be? 1. So in order to predict that using a linear model, we need to somehow make it understand that the predictions have to stay within 0 and 1. So the mean that we are trying to predict, and each person will get a different predicted mean based on their values of the predictors, that's what's being transformed within the model. It happens inside the machinery. Likewise, counts is the next unit after this, probably first week of March or so. Counts are discrete. What's the lowest count you can have of something? How many times have I been asked to go to jury duty, right? No. Too many, but what's the lowest time? 0. What's the maximum count? I don't know. I don't want to find out. But you can take the mean of a count distribution, and the mean might be something like 4.7, right? No one wrote down 4.7, but the mean is that. And so we still have the same issue in terms of the conditional mean being bounded, but only on one side. So that we solve with a log link instead of what we're going to do today is logits. So links take data conditional means that are bounded somehow, and they make them unbounded. That's the big picture. And all of general linear models, ANOVA and regression, the stuff we've been reviewing, technically is nested under these generalized linear models if you say that they're using an identity link, which means times 1. And I have for you a real-life example, bummer, of an identity link. This is a scratch-off ticket, a lottery ticket. In my family, this is a tradition to put in our stockings when we celebrate Christmas. Everyone gets scratch-off tickets. Yes, even the children. This scratch-off ticket was from South Carolina, actually, because we spent Christmas there 2 years ago. And I was all excited because I won $10. I got a bingo. This is my favorite kind of scratch-off because it takes like 20 minutes to go through it. So it's, you're not really trying to win anything. You're just paying for the entertainment. But this says, I get a bonus multiplier of my winnings. You know what my multiplier was? 1. Come on. Yeah, technically that's a multiplier, but that is not cool. So yes, I saw this and I took a picture of it on Christmas morning because I was like, oh, this is going to be a great example of an identity link, because that's how my brain thinks. And my family's like, what are you doing? So yes, a real life bummer of an identity link right here. The third part, you already know, the linear predictor. How the fixed and random effects, they count in this too, combine to create a predicted outcome. It's the same. So all the things you learned, like what's an intercept? Expected outcome when the predictors are 0, that's still what it's going to be. What's the slope? Change in y for a 1 unit change in x, that's still what it's going to be. All of it works the same. The catch is that it's not y anymore. It's link transformed y. So we have to get used to saying the expected logit or the expected log count. So the rest of this class is focusing on what the hell is y. The x side is the same as ever. The only other catch in terms of estimation that you should be aware of is that in standard regression, the fixed effects don't have to be searched for. Once you know all of the variance components in a model, there's a formula by which they fall out. In these models, they have to be searched for. So in terms of trying to figure out which parameters make the data the tallest, all the slopes count. That means that if you have a model with a ton of predictors, that can be difficult to estimate. So just be aware that these models may take longer to run than your standard models. So let's start with binary, because it's the easiest one. And it's the basis of a bunch of other models. So let's say I have an outcome that's zeros or ones. That means what I'm trying to predict is the probability of any subject having a 1. So I might start with an empty model, in which case I give everybody the same probability, and then maybe I add a predictor for group, and then I have 2 different predicted probabilities, and then so on. So we're predicting the probability of a 1 conditional on your predictors. So if I fit a regular GLM, the probability of a 1 is what I'm predicting. Beta 0 would be the expected probability of a 1 when all my predictors are 0. The beta slopes would be the expected change in that probability, and E would be the difference. So let's say that I have an actual value of 1, my predicted probability is 0.6, E would be the difference, 0.4. So what could go wrong? Well, a lot of things. Number 1 is the boundary issue. So if I fit a linear slope of x, it's going to keep going no matter what. It's going to predict a probability of 1.4 eventually, or negative 1.4, and that's not cool. So we need to take this line and squish it, make it bendy. And the shape of this S shape, is known as a logistic curve because that's how it got created. So the way this happens is a link function. Your brand new friend, step 1 is to take probability and turn it into a quantity called odds. It's the probability of a 1 divided by the probability of a 0. That's what odds is. And can we all agree that a numerator and a denominator make a ratio? This is not an odds ratio. That's a whole separate thing. And that's really, really confusing. So we have probability of a 1. First step here, translate that into odds. So the new scale of odds is bounded by 0 at the bottom and positive infinity at the top. So it's only halfway continuous. We still have a boundary issue. It's weirdly asymmetric. So if the probability of a 1 is 0.7, then the odds are 2.3. If the probability of a 1 is 0.7, that means the odds of a 0 instead are 0.4. So I find this scale not helpful and not intuitive. So some genius figured out how to fix it by taking the natural log of the odds. And that is our new best friend, the logit. People call this log odds. People call this logits. I had a graduate student tell me that it should be the logit because you don't take the log of it, you take the log. Therefore, it is the logit. Not wrong. That sounds perfectly reasonable to me. So this thing is magic. It's unbounded. It ranges from positive to negative infinity, and it's symmetric around 0 as the neutral point. So if I have a probability of a 1 that's 0.5 and a probability of a 0 that's 0.5, that creates odds of 1 inside here, and the log of 1 is 0. So the mapping of logits to probabilities looks like this. So a logit of 0 corresponds to an odds of 1 and a probability of 0.5. If the probability is 0.9, that corresponds to a logit of 2.2. And I know then the opposite of that. If the probability is 0.1, that's a logit of negative 2.2. So it's symmetric. If you know the probability on one side, you know what the logit is on the corresponding opposite. So if the probability is 0.99, the logit is 4.6. Can you guess what it would be for a probability of 0.01 instead? Minus 4.6. Okay, this is a really important concept. I know you all know how to multiply by negative 1. But certain model parameters are going to predict the probability of a 1, And in other ways of phrasing the model, they predict the probability of a 0. But because of this property, if you're given one, you know what the other has to be. You multiply it by -1. Predictions that refer to the probability of a 1 are intercepts, like as part of the model. The probability of a 0 instead is what's called a threshold. And yes, this is the same terminology as you had in the SEM class. So logits is what the model's predicting directly. But when you back translate it into probability, the probabilities stay between 0 and 1. It's magic. Here's another mapping. I like this one. I stole it from my multi-level textbook I use in the clustered class. The top here is probability scale, and then the lines show what the corresponding logit is. So an equal distance in logits does not translate into an equal distance in probability. So if I talk about a slope in logits as the change in the logit for a 1-unit change in x, I can't say anything about the change in probability because it depends where I am on the probability scale. As you get closer and closer to the boundaries, the changes get smaller and smaller and smaller. So the distance between a logit of 1 and 2 is much bigger in the probability scale than a distance between like 4 and 5 or 5 and 6. But logits go on forever. So these are the 3 versions of y that you will see. Probability, where neutral is 50-50, translates into odds of 1 as neutral, translates into logit of 0 as neutral. So this is a definition thing. Memorize this. And I always like to do, I get my stick out, pretend I'm a conductor. A logit is the log of the odds of the probability of a 1. Can we say it with me? Humor me? The logit is the log of the odds of the probability of a 1. There we go. And it's always a 1, damn it. I'm going to fix the model whenever they try to give me zeros instead, because that's just unnecessary. Okay, just memorize this, okay? So these are your neutral points. There's a non-linear relationship between the two, and that's the key thing here. So that's one problem. Logits solve the boundary issue. They are going to ensure that our predicted probabilities stay between 0 and 1 like they're supposed to. The other issue, though, is this idea on the variance side. If we fit a regular general linear model to a binary outcome, E can only be one of 2 things. Right? If you have a predicted probability somewhere in the middle, you're either wrong by this much to get up to 1, or you're wrong by this much to get down to 0. So there's only 2 possibilities for each possible predicted probability. That can't yield a normal distribution. It can't. And not only is it not normal, but the variance has to shrink the closer the predictions get to their boundaries. There's not as much room to be wrong. So a binary variable has a maximum variance if its mean is 0.5, and it shrinks as you move away from that. So in the normal distribution, we say normal with constant variance. That can't work for binary data. So we're going to not pick normal. We're going to pick something else. And here's a comparison of the 2. So the normal distribution, I stole this from Wikipedia, of course, has 2 parameters to it, mean and variance. They're separate. This is the formula. It's one of the ugliest ones. But everything in it is a function of mean or variance. So we have predicted mean here, and then variance. That's a 2. That's pi. That's a number. The rest of this. That gives me the height. So instead of using this formula for height, I'm going to use this one. And it's the simplest one there is. It's the probability of a 1 if that's what you have, or the probability of a 0 if that's what you have. The end. So this Bernoulli distribution is for binary outcomes with only 2 choices. So I know that if the mean, for instance, is 0.75 in this group, I know it's 0.25 over here. And I know that the error around it is not constant, and it will shrink with the mean. Because in the binary, the variance is the mean times 1 minus that. That's where it comes from. So this side is not about the boundaries. This side is about getting the right inferences, the right standard errors, and the right confidence windows around your stuff. Here is why this gets confusing. There are 4 equations on this page, right? They're all equal. They're different ways of saying the same thing, and they differ in what y is. So I like the top one. This is predicting the logit. The log of the odds of the probability of a 1. Yes. Once you get your head around that, this is perfectly normal. Beta 0 is the expected logit y when the predictors are 0. Beta 1 is the change in logit y for a 1 unit change in this variable. They work the same. It's gorgeous. It's beautiful. The problem is like, okay, my model has a predicted logit of 2.4. What the hell is that? Most people don't have a ready sense of what logits mean because they're not. I can tell you if the logit is positive, that a 1 is more likely than a 0. And if the predicted logit is negative, that a 0 is more likely. I can tell you that, but I don't have an intuitive sense of that. So if we back it down 1 level, we take the log part off, unlog it, as I tend to say. I believe the correct term is exponentiate. But unlog it works. Then we express the model this way, and our nice linear model gets put into this exp function. This one breaks my brain because you end up multiplying these terms together instead of adding them, and I can't handle that. I also don't think odds are that interpretable, so I don't like this middle one very much. I skip over it usually. But then we get down into probability. And probability is a nice, natural way to interpret things, right? If I told my mom there's a probability of 0.8 that I have to have jury duty, right? She knows what that means. If I tell her that I have a logit of 2 about my jury duty, she'd be like, what the hell's a logit? But then the rest of the model has to look like this. And you can't talk about these slopes in any kind of standard way. It doesn't work. So who's in the IRT class? Few people are? Anybody? Okay. This is the way IRT models are written. That's why they look so crazy. But you can write them this way instead if you want. And they look nicer. Except for the minus signs. But that's coming. And this equation you can write more shortly. Is that a word? More succinctly? More compactly? If you stick a -1 down here. So in my formulas and things, you'll see me write this version just because it's less typing. So -1, I call that the not model. But here's another thing that you should try to commit to memory. This transformation to go back to probability from logits, it's called an inverse link. So link functions go from the scale of the data up to the link function, like from probability up to logits. Inverse link is coming back down. So to get from a predicted logit to a predicted probability, it's e to whatever the model says the logit should be, that's the interior part, over 1 plus e to what the model should be. So you'll hear me say this a lot, e to the logit plus over 1 plus e to the logit. That's this formula. That's another one just to commit to memory, to go back and forth.
Is that what margins is doing under the hood?
Yep.
Okay.
Yep. Yeah, this is something that you don't have to do. You can ask software to do these conversions for you in many cases, but I will make, like for pedagogical reasons, I have formulas and things, and I have to do it in R sometimes too to make it myself. So e to the logit over 1 plus e to the logit. So that's why all of these things look different. They're predicting a different version of y on a different scale. And if you're like, is this logistic regression? Yes, it is. That's what normal people would call it. If you approach it from like the Mr. Potato Head, Lego perspective, then I would call this a linear model with a logit link and a Bernoulli conditional distribution. The rest of the world calls this logistic regression. Take your pick. So here is a mapping of what you can and can't do in terms of moving back and forth between logits and probabilities. Let's say I have this model. Then what the model is predicting directly is in logits. So y hat here, predicted y. I can take that predicted logit and I can exponentiate it down to an odds. So then the neutral point, remember in logits, is 0. The neutral point in odds is 1. And then I can further translate that into probability if I want, where the neutral point is 0.5. You can do all of these things. So you can express the model predicted outcome in any of these 3 scales you want. The slopes, however, you cannot. So this slope is in logits. You can only talk about it as a 1 unit change in logit y per unit change in x. To exponentiate that slope creates something called an odds ratio, which is a ratio of odds, like 2 fractions stacked on top of each other. That is an effect size. That is by far the most commonly used effect size, and it shows up on your output in readily form. But you cannot take this slope and try to convert it into something that talks about a 1 unit change in probability. You cannot. It does not work. The reason that it doesn't work is this picture right here. A 1 unit change in logits does not correspond to the same unit changes in probability. So the best you can do with your slope is to just stop at odds ratios. Don't go further. So order of operations then is very important in generating predictions accurately. Step 1, use the model in logits to compute a predicted logit. Then translate that predicted logit into predicted probability. You cannot translate the slopes directly. Okay. Want to see a start of an example?
Yeah.
Yes. Okay. Numbers. People usually like numbers. This is example 2A. This is fake data. I stole it from a website. Here's the website I stole it from. But the reason I stole it is because now you can have the data. So I try to build examples with public data when I can, except unless I have something specific I want to emphasize in real data. So I took what used to be an example of an ordinal regression and I dichotomized it so I could make an example of binary. That's why. Don't ever do that in life, okay? Don't cut up your variables like that. Just, I had to do it for this. So we are going to predict a binary decision of how likely they are to apply to grad school in an undergraduate fake sample from their undergraduate GPA on a 4-point scale, a binary predictor of whether at least one of their parents has a graduate degree and whether they attended a private university. So I have notes here about what I'm using with respect to the various packages. We have not talked about the correlations yet, so I'm going to skip over that for right now and we'll come back to it. So step 1 in Stata, load the data. This data set did not have an ID variable, so I made one. That's how I know it's not real. They made it up. I am renaming the variable that they had called apply to apply 3 to remind myself that that's the version that has 3 categories. And then I created a new one called apply to that initializes to missing data and then recodes it into binary for 0 is 0 and then greater than 0 is 1. So it was like the choices were, how likely are you to apply to graduate school? Like no, maybe, and yes. And so I'm collapsing the maybes and the yeses. So it's like the decision is absolutely not or maybe. I also renamed their predictors to be a little bit more standardized. So parents, whether or not they have a graduate degree, where no means 0 and 1 means yes. And then GPA is a continuous predictor that I centered at 3 because that was the mean of the sample. I also switched the reference group for public versus private university so that public is the, public was the 1 previously. I wanted it the other way so that the slopes would be positive. I thought this is hard enough if I have a mixture of slopes. And so here's the variable labels, and then limiting the sample to just complete cases because you have to do that in reality if you're going to have models with different predictors, even though there's no missing data here. Same thing in R. I found this code to make an ID variable. It means I stole it from somewhere on the internet if you see this symbol, because I always use equal signs as God intended. And then we're making the same recoding process here, centering process and whatnot, and then filtering. So, first things first, descriptive statistics. The mean of this variable is 0.45. So, what proportion of respondents have a 0? 0.55. That means what proportion have a 1? 0.45. So you need to know this so that you can tell what your software is doing. In SAS, the logistic regression defaults to predicting the 0. I know. Why would they do that? So ever since then, that's the first step, is to fit an empty model so you can figure out which way is up and what it's predicting. And knowing this number out of the data is how we can make sure we're right. Not going to talk about correlations yet. So we're going to skip over those for right now. Haven't got there yet. So here is our first model, an empty model. And the research question being answered is, which value is the model predicting, the 0 or the 1? It's an important research question. So writing this out long form, the log of the odds of the probability of a 1, I'm going to shorten it to look like that. But technically, it's this whole thing is what y is. And an empty model has no predictors. It only has a fixed intercept. So if I don't know anything else about you, what's my best guess for your outcome? What's the meaning of beta 0 in this model? If I don't know anything else about a person, what should my best guess for their outcome be? The mean, right? So that's what this is going to tell me. It's going to tell me the mean in logits, but then I can e to the model over 1 plus e to the model and get the mean in probability, and it better match what I just found in my frequencies table for the proportions. So that. This is the model predicted logit. It's just beta 0. What's normally in my equations that's not here? And it's also not in any of these formulas. Error. It's not here anymore. Not because it's perfect, but because it's not an estimated parameter. So these models don't have e's on them when you write them out. No, we're not doing thresholds yet. Okay. So in Stata, I'm using the command logit, which is for binary outcomes, so you don't have to tell it anything more than that, and my binary outcome is apply to. No log just shortens the output. It doesn't print all the iteration history, so it doesn't get as clunky, that's all.
The only default is that is if your model's not behaving properly, sometimes it just runs and runs and runs, and you don't notice that it's running and running and running.
Yeah, it's just hanging at that point then. So yeah, for troubleshooting purposes, you might want to turn that off.
And I will say, with all of your homework, I have never run into that problem. It's usually my own messy data.
Yeah, well, fake data is very well behaved, usually. Not always, though. But I have had instances in which a data set I generated in SAS caused R to throw up or something in fitting the population model. That has happened. So. Hmm? Say it again? No, it should work. Like the. Why no errors? Oh, in the model? Because the idea of E is to represent its intended parameter. So E is the idea that we have an error variance in the model. We don't have an error variance in the model anymore. There is no such thing as residual variance in these models. It's fixed to a number. That seems arbitrary, but I'll tell you why. But it's not there. So this model has one parameter, the intercept, that's it. Because the Bernoulli distribution has one parameter, the mean, and that's it. That's why. So, new things that you're going to see. The output looks somewhat different than what you're used to. No more sums of squares table. It's gone. You'll never see it again this semester. It's gone. Instead, you will see things called log likelihood, as what you get in Stata. And I'm asking here with this little command to take that number that's stored internally and multiply it by -2. Then it becomes this number on your output. Here's why. This is my new way of checking if you have the right model in your homework. It's a thumbprint for your model. If you get this number right, you have the right predictors and you have the right outcome. I'm going to ask for it in this form of -2 log likelihood, in which smaller is better. So this would be the number that you put in, -2. The reason for that is because these numbers have no absolute meaning. They're tied to the scale of your outcome, but they have relative meaning. And it turns out that the difference between them, if you multiply that difference by 2, is distributed roughly as a chi-square. And so it forms the basis of a test statistic. So the multiplication by 2 to start with, -2 to make sure that it goes in the right direction, is to save you a step. So then you can take the straight difference, but we'll do that in the software. Another thing that you will get is information criteria, is what these are called, AIC and BIC. Akaike, I think, is how you say the first one, and the Bayesian information criterion. These are used to compare non-nested models. They also have no absolute meaning. They're sample and data specific, but they have relative meaning. So we can look at these indices becoming smaller as evidence that our model is better as well. So the only thing in our model right now is _const. Do you remember what that means, Stata users?
Fixed.
That's my fixed intercept. And I really don't like that they call this the constant, because all fixed effects are constants by definition. But no one asked me. So I'm predicting the probability that someone is going to apply to graduate school. And my answer here is -0.2. Did I mess it up? Did whoever programmed Stata mess it up? No. What scale is this number referring to? There's 3 choices: logits, odds, or probability. These are in logits. So what does a logit of -0.2 correspond to? I know that it's negative, which means that zeros are more likely. That's what a negative logit means. Here, e to the logit over 1 plus e to the logit corresponds to a probability of 0.45. We saw that number before, right? That was the proportion of people in the sample that have a 1. Therefore, now I know that Stata's logit command is predicting the probability of a 1, not a 0. What is the probability of a 0 instead? You told me this earlier. 0.55. What is the logit of the probability of a 0 instead? 0.2. This multiplied by -1. So I'm going to ask you homework questions where something about the probability of a 1, and the next question is going to be probability of a 0 to reinforce this concept. And I learned the term for this, apparently, multiply by -1 is the additive inverse. Some math people told me that. So I figured there had to be a term for it. So now I know what my software is doing. Hooray. We have not talked about this yet, but this is going to be your new analog to the F-test for the model. This is a model comparison against a model with only an intercept. This model has only an intercept, so the comparison is 0. Also note, we have coefficient, standard error, new letter, Z. What letter is normally in your tables? T. What's the difference? No denominator degrees of freedom. So this model does not care how many people it's being estimated on. It's using Z under an infinite degrees of freedom assumption. So probability of Z is what we get to go with that. Margins is a command that allows you to generate predicted outcomes. And so I literally just typed that one word and it spit out the predicted outcome, because in this model, the same probability is predicted for everyone. So it's generating predictions in the probability metric by default. You can ask for predicted logits, and I have that later in this handout. Okay, let me zoom back out and make sure I said everything that I wanted to say. I think I did. Yep. Okay. R folks. Today, I'm using a base R package called GLM. Throughout the semester, there will be many, many R packages used. The documentation for all of them, by the way, I have done that for you because I had to do it for myself anyway. On our course webpage, in this box, these are all the different packages we're going to use and the documentation for how to use them if you need to get to that. So a lot of different things, unfortunately. But GLM today. GLM stands for Generalized Linear Model. It wants to know what your data are. The model itself, formula, looks exactly the same as an LM. The middle part here is new. So because this is a general modeling function, you have to tell it what kind of generalized model you want. And I want link equals logit within the family binomial. Binary is a special case of binomial when there's only one trial. Binomial is multiple trials, like number correct or something like that. So R labels this intercept, thank you, and it gives these things, null deviance and residual deviance. And I figured out through trial and error that the first one is always for the empty model and the second one is always for the current model. So these are the values given directly that you would put into the homework system. These are -2 times the log likelihood. It gives you AIC by default, but not BAC. So I asked for that to get them both. And I couldn't make it do predicted outcomes very efficiently, so I just wrote it myself. So this is an example of the shortcut formula. I am making a new object called model2 empty, model for binary data, that's what the 2 means, empty model probability, 1 over 1 plus e to the not logit. So this is from that formula. I'm writing that formula in R to make it make my probability and then spitting out the result, and that's what I get to the 0.5. So now we know about our model and what's being predicted. Okay, how we doing? Want to see model with stuff in it? Why not, right?
Can you tell everyone why we need to know A1C and B1C?
We don't have to know them, but as you're looking at a series of models, they are indices of how good a model is. Smaller is better. So if you add things, you might want to see that these go down as well. Here's a model with some stuff in it. To what extent do undergraduate GPA, parent education, and undergraduate school type uniquely predict the probability of applying to graduate school? So this part looks the same as usual because I'm writing it to predict the logit, and that's how the model's being estimated on logits. I'm centering GPA at 3, and I have C dot in front of all of my predictors so that it's treating them as continuous variables. I did the dummy coding myself. I don't need it to do any of that for me. Note this over here has moved. LR chi2. That's data for likelihood ratio chi-square. This is a model comparison against the model we just estimated. It does it for you. So 20.59 is how much taller this model made the data relative to the previous model. The p-value goes with it. So this replaces the f-test for the model that we had in Sums of Squares land. You can also ask for f-tests through this, but they use denominator degrees of freedom, which Stata doesn't do. So you would have to ask for a multivariate Wald chi-square, and I have found through trial and error that that differs across programs more than this. So I switched to this. Okay, let's try the coefficients. Starting here. That's my fixed intercept, right? Intercept always has the same definition, expected outcome when your predictors are 0. So let's do the easy part. When are my predictors 0? Who is the expected outcome for? Yep. Whose parents don't have a graduate degree and who went to public university instead of private. Okay, that person has a predicted outcome of minus 0.54. In what metric? Logits. So the logit of the probability of applying to graduate school in the reference person here is minus 0.54. Now, GPA. Who's feeling brave? Want to put the number in a sentence? .55 is the slope. Positive.
Improving your GPA by 1 point would lead to a 0.55 increase to your logit.
To the logit, yep. So a 1 unit improvement in GPA corresponds to a 0.55 improvement in the logit of the probability of applying to grad school. What's logit again? Log of the odds of the probability of a 1. Okay. How about if your parents have graduate degrees? Are you more likely to apply to graduate school or less? More. You can look at the sign the same way as usual. Positive slope means more likely to have a 1. Negative slope means more likely to have a 0. So the logit is higher by 1. What if you went to a private college instead of a public college? Yeah, a little higher, not significant. And do I care if the intercept is significant? Not usually. But in this case, it's telling me that the intercept is not different than 0, which corresponds to a probability of 0.5, or a logit of 0 in this case. So could be of interest, not usually. So yeah, the tricky part is figuring out what y is. The rest of the model works the same. Here's my new minus 2 log likelihood. And that number, minus the one from the previous model, is what I get for me right here. It does it for you in that case. All right. We have not talked about these yet, but do you remember when I told you R² is gone? I didn't exactly say that correctly. Here are 17 kinds of R²s. This is the one that Stata uses by default, and it prints it at the top as pseudo R². That term means ish. So here's why I say R² is gone. Which one of these is right? R² is somewhere between 0.02 and 0.07. And I've seen it vary even a lot more than that in practice. So if you want to use any R², you'll probably have to say why you picked the one you did, or at the very least say which one it is, because there's like 17 of them. So we're not doing that. We're not doing that. How about some predictions to make some more pedagogical points? We saw this in margins. I'm asking for predicted outcomes for somebody with a GPA of 2 in increments of 1 up to 4, because we're centered at 3, holding these two constant. And then predict XB says make it in logits. So these are the predicted logits at a GPA of 2, 3, and 4. And you'll note the difference between them is exactly the same. because the slope in logits says the change is constant for every unit you move up in the predictor. So moving from a GPA of 2 to 3 in logits is the same as moving from 3 to 4 because GPA has a linear slope. If I ask for the same prediction, not in logits, if you leave that off, it changes to probability. Then we get predicted probabilities. So the probability of applying to graduate school for a GPA of 2 is 0.25. It goes up to 0.36 and then up to 0.5. So the differences between those predicted probabilities are not constant. That's why we can't talk about a slope in terms of what it does to probability. It does not work that way. So your slopes can talk about changes in logits, or they can talk about changes in odds, but they cannot talk about probability. To talk about changes in odds, we would estimate a different quantity, which is the odds ratio. So if you add that to your logit command, you get this instead. This is the unlogited version of your slope, the exponentiated version, and that's an effect size. So as I noted out here, it's e to each of these fixed effects. So those are going to be effect sizes, which we haven't talked a lot about yet, but I wanted to show you some numbers. R folks, I didn't forget you. Here's your model. Same results. We get, it does not do the likelihood ratio test for you, but you can. I'm getting confidence intervals around my logit parameters as well. And I am doing the likelihood ratio test that Stata did for me. So it uses a command called ANOVA to do this, which is the worst named command ever because it has nothing to do with analysis of variance at all. It does likelihood ratio tests. So what it wants to know is, hey, what are the two models to be compared? Model empty and then model main. These have to be in this order. The model with fewer parameters goes first. The test that I want is called LRT. Apparently there's more than one kind. So then it reminds you what models are being compared. This quantity right here labeled deviance, that's your test statistic. That's analogous to the F-test for your model in regression. It's analogous, but it's a chi-square. So the 3 slopes that I added significantly improved my model. They made my prediction, my predicted outcome significantly correlated with that one, and there's the p-value that goes with it. It would be written like this in practice, either the difference in -2 log likelihood as what the test statistic is called, or some people just shortcut it as a chi-square. Inside the parentheses is the number of terms different between your models. So my first model had only an intercept, and my second model added 3 slopes. That's why it's a 3 in here. And I asked for R square in R, and here's like 17 of them that way. And there's even more than this, right, Vladimir? You had found other ones too after this. So yeah, there's even more than this. And they vary in how much. This one thinks R square is all the way up to 0.08. I'm going to pick that one. There's a command I found called odds ratio that will make those. If it doesn't work, here is another way to do it. I had some folks not get it to work for whatever reason. And the same logic of prediction. So I'm asking for it to predict GPA from -1 to 1, which on the centered scale is 2 to 4, to make the same point that the difference in predicted logits is constant, but the difference in probability is not. So the difference between these commands right here, type equals link, you'll see that across the examples. That means put it on the scale that the model is directly estimating it in, like in logits. Type equals response is the inverse link, back translated down into what the conditional mean scale is, probability. So these are predicted logits, these are predicted probabilities down here. All right. See, that's not so bad, right? It is at first, I know that, but you get used to it. You do get used to it. All right. So one of the things that you will see, going back to the slides for a minute, this is slide 14, is this number pop up in random places, 3.29. In a lot of the formulas to compute R-square, that is what is used for residual variance in a logistic model. The reason for it is connected to the idea that if I'm using a logit link, another way to explain that is that I think underlying my binary variable is a continuous variable. And it has a logistic distribution which looks like these shapes here. In binary data, the variance of a logistic distribution is pi squared over 3, or 3.29. So in various places, such as I saw in the state apart, you go back to this, right here, variance of error, it says it's 3.29. Guess what it was in the empty model with no predictors? It was 3.29. It will always stay 3.29 no matter what. It's fixed. So we don't have a true R-square because of that. So this version of the model, Y star, you will see people write it this way, has the E in it because this is predicting the pretend underlying variable that we don't actually have. And that has an E with this variance. Do you want to do probits? Yeah, we'll do probits. Okay, here's another link function that you will see and should know about. Probits. You've heard of logits, now we have probits. A probit is a z-score. Do you remember back in intro stat, like your very, very first stat class, and you had a textbook maybe with like tables in the back, and they had like z tables and that corresponded to probabilities and stuff? That's this. The probit link is the z-score that goes with that probability for the area to the left. So probability of 50-50 corresponds to a z of 0. And then you would calculate, like if you had a probability of 0.8, what would be the z-score that goes with 0.8 as a probability? That's what probit is. If you are in the IRT class, what is probit called? It starts with an O. O-G? Ogive. Probit is ogive. So they use that there too. The difference is in what we think this shape is. Probit is like, it's not logistic, it's normal. Okay, so if it's normal, then the E variance is 1 instead of 3.29. So here's what it would look like in a mapping of a distribution where the mean is at 0 in logits, and the pretend underlying continuous distribution that gave rise to these binary things. This is pretend, okay? That pretend distribution has a variance of 1 in probits and a variance of 3.29 in logits. And if you're like, but it's pretend, how can I know if I'm right? It doesn't matter. Because once you correct for this difference in scale, logit coefficients are equal to probit coefficients times 1.7. And certain people think it needs to be 1.701. They're probably right. But once you make this conversion, do you see the difference between the red and the black lines in here? Not much. The predicted probabilities are the same. So that's a long-winded way of saying logits and probits do the same thing. They both take probability that's bounded by 0 and 1 and stretch it out onto a continuous thing that's unbounded. The continuous thing is on a different scale. It has a variance of 1 in probits or a variance of 3.29 in logits. So it doesn't really matter which you use, but there are certain situations in which you're forced into one versus the other. So that's why I want you to know both. In probit land, there's no such thing as an odds ratio because it's not made of odds. So in my examples, I have a couple Probit models just to show you what that would look like in terms of converting back and forth. But it does work. The predicted probabilities match to like 3 decimal places. So. All right. And yeah, I don't know where I stole this slide from, as noted, but I'm pretty sure I stole it from Don Hedeker. So thanks, Don. He's my hero. You'll hear me talk about him a lot if you listen to me. All right, 311. How we doing, folks? Stayed awake. Good work. Everyone stayed awake. Good work to all of us. Gold star, yes. So, any questions as we wrap up for the week here? Then, please finish your homework on Monday if you can. If you don't get it done in time, it's a 2-point deduction, but you got 2 extra credit points for doing homework 0, so it's okay. And also, each question is worth just a tiny fraction of a point, okay? I don't know how many questions there are in this one, like 80 or so? Maybe more than that?
A lot.
A lot. Yeah, there's going to be a lot of questions. There's going to be. So each one is worth a tiny fraction of the overall, I think it's worth 15 points maybe altogether, something like that. That means if you get stuck on one answer and you can't get it, it would be better to leave it blank and turn it in on time. Because what will happen is that you will get the correct answer back after the due date passes, and you can see what it should have been and try to work backwards and figure it out. So that's my advice, is don't be a perfectionist. If you're up against a deadline, try to get as much of it done as possible and just submit what you have, unless you're going to lose more than 2 points, in which case it makes sense to do it later. So you just have to get it done by the end of finals week. That's where the door closes. Okay? All right. So then, watch your email on Monday night for me to let you know who's coming on Tuesday and where you should be. We'll hope it's me, but we'll see. So, thanks for being here. See you on the other side. Bye, Zoomers.